Let's now solve an example involving random pulses occurring on a structure with no degradation and a known number of pulses. So let's take a minute to read the problem, and then we will go through the solution. Okay, so clearly the problem has been stated to confirm very closely with the case 3 that we just presented, that C is time invariant and the loads are IID, also independent of the capacity, and they occur as pulses, and the number of pulses in the duration T is known. There's also another interesting fact here, that the loads are type 1 max distributed or Gumbel distributed. We're going to take advantage of that soon. So this is our starting point. The reliability is the integration of the CDF of the load evaluated at an arbitrary capacity raised to the power of n being the number of pulse occurrences, and integrated over the with respect to the capacity. Now this is also the kernel inside the integration. Fq to the power of n is nothing but the CDF of the maximum load. It's something we will look at in some other context, but it's good to know that the maximum of n IID random variables has a CDF which is the parent CDF, the individual CDF raised to the power of n, when there are n quantities, n random variables whose maximum is being taken. So let's see if we can do something with this Fq to the power n. Let's focus on the fact that Q is Gumbel distributed. So now we just write out the CDF of Q and raise it to the power of n, and then the algebra is going to actually help us simplify. We can bring the exponent down into the first exponent, nt, so nt multiplies with the second exponential, and then we can put it in the exponent in the logarithmic form. So we have in the second exponent log of nt minus alpha times x minus u. Alpha and u are the parameters of the type 1 distribution for the individual loads. Now this we can make a clever substitution. We can make it look exactly like the Gumbel form, but change u to u sub n. So now u is a function of time through the number of occurrences within the time. So it's given in terms of u plus log of n divided by alpha. So u with more number of occurrences shifts to the right, and the original u, you add log of n over alpha and get the u for the maximum of n. So the Gumbel family is closed under maximization. That's actually the reason that we could write this way, and we are left with a Gumbel form with the same alpha but a different u, a larger u, and that increment depends on n, the number of occurrences. So in effect, once we start Monte Carlo simulations, we will end up basically evaluating the expectation of this fq to the power of n. One interpretation could be that as well. So now let us describe the code. I have coded it in just in a few lines, trying to go through the first principles of the formulation. So in the first block, I define all the parameters of the random variable c, the parameters of the random variable q, and also just define how long we are going to run the simulation. So I'm going to do it for 100 years, and the time interval that I will estimate reliability is 1 year. So every year I'm going to find out what the reliability is. I initialize the problem. There will be 100,000 simulations, and I set r equals to 1 at t equals 0. So that's just setting the boundary conditions. And then I start with the tau loop. So the outer loop is on time. So tau starts from delta tau all the way up to t max. And there's a reason for doing that, because if tau is 0, I will not be able to take the logarithm of that, which would be a problem. So that's why I start the for loop on tau, not from 0, but from delta tau. In the last line that you see in the block is I have defined the u of the max. So it's u and t. So that's what you see. For each value of tau, I define the corresponding u tau or u n tau. Then the inner loop is the Monte Carlo simulation loop. So for each value of tau, I run the simulation 100,000 times in this case. For each Monte Carlo trial, I generate a value of c. I generate a value of q tau. So it's basically the maximum load. And then I have the if block to check whether my structure survives or not. So if it does, I increment the count of reliability by 1. And once I am done with the Monte Carlo loop, I can estimate the reliability at time tau by dividing the count by number of trials, and the last end is the end of the tau loop. One point to note is that I deliberately put the time loop outside and the Monte Carlo loop inside. That makes it very straightforward. If you change the order of the loop, it will be a lot more complicated. So this is much preferred to have this order of the loops. So once the program runs, and again, this is a very simple schematic, we could have a much more complicated structure. Each such call to the if block might require a finite element program. The load itself might be the result of some other process, so it would not be as simple as generating a Gumbel random variable, but this would be the core logic of the simulation. And let's see how the results look like. So we have a reliability function that starts from 1 and slowly drops off to lower and lower values. Obviously, something like a 60% reliability is too low for a structural member. But this is just for illustration purposes. If it was a real structural member, then we probably would need to redesign this structure.